All right, in the last few videos we've talked about charges and charging. In this video we're going to introduce the concept of the electric field, which is what charges actually produce. So you're probably familiar with the idea that if you have like charges, they tend to repel, and if you have unlike charges, they tend to attract. And that brings up this concept of force, which is really the interaction between pairs of charges in this case. And you might be wondering, well, why aren't we talking about force? Why are we bringing up this idea of the electric field? And the reason is that the electric field and fields in general are in some sense more fundamental than the concept of a force. The idea of a field is that it can be due to a single charge or a collection of charges. And it is the thing that actually mediates the interaction. It mediates the force. So we're going to introduce this concept of the electric field by starting with sort of the simplest example, which is a single point charge. So a single point charge is also sort of an abstract construct. It's this idea that you have some amount of charge and it's crushed down to a very, very small point. In our case, we'll deal with a plus charge, some positive charge. Now, what we observe is that at some other location away from this charge, there is an electric field which points radially outward, directly away from the charge itself. And this happens in all of space, everywhere, except at the location of the point charge, where it's not defined. Now, what becomes important is actually where we are observing this electric field, as we'll see in a moment when we start to mathematically describe this. And the thing that's actually important is the vector which points from the charge itself to the point that we are observing the electric field, which we'll refer to as the separation vector. And it'll become clear why we call it the separation vector in a moment. So mathematically, if we're going to try to describe that electric field, when we go out and we measure the electric field due to that charge at a variety of locations, it turns out that the electric field of that point charge fits very well to this mathematical description, which we'll unpack here. So this is the electric field due to a point charge. The electric field has units of newtons per coulomb. That's force per charge. And that'll make sense when we start to talk about the electric force and how it's related to another charge that is in the presence of this charge and the electric field that source charge produces. So there's a bunch of pieces here, so let's unpack those. So this first piece, 1 over 4 pi epsilon 0, is a constant. It describes how strong the electric field is relative to other kinds of fields, gravitational fields, magnetic fields, and so forth. But for our purposes, it's just a constant that we're going to keep track of. Okay? The Q up here is actually the charge that we care about, the charge that is producing the electric field. It can be positive or negative. It can be 1 coulomb. It can be 10 microcoulombs. It could be any value that we desire. So this is actually the charge. Now these guys, r squared and r hat, are related to this separation vector. And so let's spend a little time talking about those because they're a little bit more complicated than the other pieces of this formula. So if we were going to describe the separation vector as some location that we're interested in relative to the charge itself, this is just a vector in the same sense that you've seen in mechanics. So the magnitude of that vector is just the sum of the squares of the components of it, square root, right? So when we take the square of that, it's just the square of this magnitude. It's just how far you are away from the charge squared. This guy, r hat, is the unit vector. And it describes the direction of this vector. And it's a little bit more complicated than the magnitude because it includes both the vector itself and its magnitude. So it's taking the vector itself and dividing it by its magnitude. Now this unit vector always has magnitude 1, and you can see that if you take the magnitude of this, you're taking the magnitude of the vector itself divided by the magnitude of the vector. So it really only gives us direction information, which way the separation vector is going to point. So when we look at this, everything looks relatively straightforward in the sense that these R's represent this separation vector here. Now the challenge becomes when this charge does not exist at the origin of coordinates. It's free to be sort of anywhere in space, as is this observation location. So we haven't actually put a system of coordinates on here. So let's unpack that, because there's going to be two more vectors that show up that are important for understanding that separation vector. So we'll just draw a coordinate system. So this is the x direction, this is the y direction. And this here is the origin of coordinates. Now I've imposed a coordinate system on the measurements that we're going to make. So I'll stick a charge here, some positive charge, and it doesn't coincide with the origin of coordinates. It's somewhere else. And I'm going to observe that electric field over here. So I know from looking at the way that positive charges produce electric fields that the electric field that will be produced by that charge is going to point directly away from it like this. So the separation vector, which points from the charge to the observation location, is this one. But that doesn't tell you what this vector looks like with respect to the origin, where you're actually measuring distances. So there are two more vectors that we have to introduce. The one that points to the source charge, which we'll call R source, and the one that points to the observation location, which we'll call R obs. Now if you look at this, from the vector mathematics that you've done in other courses, you can see that if you add the source vector to the separation vector, tip to tail, you'll get the observation vector. So we can write that down mathematically as the source vector plus the separation vector gives you the observation vector. And so now we have a definition for the separation vector in terms of things that we have measured with respect to the origin. Namely, that the separation vector that we care about is always going to be the observation location minus the source location. So this guy here is actually the R vector that shows up in this equation through its magnitude and its unit vector. So you can see that if the charge itself coincides with the origin of coordinates, this goes away, and the separation vector and the observation vector are exactly the same ones. But that's typically not the case. It is typically the case that the source is some other place, not at the origin of coordinates. So we have to be careful with that. So one last thing that we'll talk about is just what the shape of the electric field is, or what the pattern of the electric field is for positive and negative point charges. So I'm going to write the electric field equation back up one more time, just so that we have something to talk about and look at. So for a positive charge, we've already said that the electric field points away from positive charge, but it also gets smaller as you get farther away from it. So when you're nearby, the electric field vector is very large. The tail here represents where I'm looking at it. That's the observation location. And the arrow represents the electric field. If I'm a little farther away, then that electric field vector is a little bit smaller. If I'm farther away still, it's even smaller. And we can draw that everywhere in space because the electric field produced by the point charge exists everywhere in space. I'll just do it like that. Now, the other thing to notice is that the magnitude of the electric field is the same for any sort of spherical surface that is the same distance from the center of that point charge, right? So these vectors, even though they kind of don't look like they're the same size, they're meant to be the same size. They just point in different directions. Now, for a negative charge, we have something that looks quite similar, except now all the electric field vectors point towards that charge. So if I'm some distance away from that charge, I have an electric field vector pointing like this. If I'm a little farther away, it's a little smaller. A little farther away, smaller still. And I can go all the way around again and demonstrate that the electric field should point inward everywhere. And again, if we were to take some spherical surface around that charge that is the same distance from the center, all the electric field vectors would be the same length. They would just all point radially inward. So this video was meant to just show you a little bit about point charge electric fields, to really demonstrate that you have to pay attention to the idea of the coordinate system that you're working with, and also to sort of demonstrate the pattern of the positive and negative electric field vectors, because those are going to come into play a lot in this course.